Okay, now we want to start a brand new chapter, chapter 5, and this is all about momentum and impulse. And these methods that we're leading to here are often used to solve collision problems or problems where you hit a ball with a bat or something like that, where there's some kind of complicated interaction between two particles. We don't know exactly what happens during the interaction, but we know what happened before and after, and by looking at the change in the characteristics of the motion, we can sort out some information about what happened during the collision. All right, so that's kind of where we're headed here. So we want to talk about impulse and momentum, talk about the impulse momentum principle and how it connects to Newton's second law, and then use this to solve a couple of problems. All right, so Newton's second law relates force and acceleration, F equals ma, and it's true at any instant. But for example, when we hit a baseball with a bat, there's some time period over which the ball and the bat are in contact, and we don't know the forces between the two. It's very complicated. So it's hard to, make use of Newton's second law, which tells us about force and acceleration. We don't know the force between the two, so it's hard to just prescribe that force and integrate over time and find the acceleration, for example. So we have to do something a little different, and that's where momentum comes in. So we can get this essentially by time integration of Newton's second law. So we start with F equals ma, and we integrate both sides of this over some time period from T1 to T2. So the integral of from T1 to T2 of f dt is the integral from T1 to T2 of ma dt. And that's true since F equals ma at any instant in time, then this is true for over this time interval T1 to T2. So ADT can be written as dV, right? dV dt is A, so ADT is dV. So this left side, which is unchanged, becomes, we can pull the mass out and we're integrating dV. So we get m times the velocity evaluated at T2 minus the velocity evaluated at T1. So this integral quantity, the time integral of force over some time period, is the change in this product of mv. Mv is momentum. So what this tells us is that this integral of the force over time tells us about the change in momentum from one time to the other, from the beginning of the end to the end of that integration. So we call this the linear momentum, mv, and we give it the symbol p. It's a vector because v is a vector. Has dimensions of mass times length per unit time, kilogram meter per second in SI, or pound seconds or slug feet per second in um, British units or US units. So this quantity, this integral of the force over time, is what we call the linear impulse. It's a linear impulse of that force F between these two times. And the units are like Newton second, pound second. So the so the impulse momentum principle tells us that the impulse is equal to the change in momentum, right? So the impulse over some time period t1 to t2 equals the change in momentum over that time period. Or the initial momentum plus the impulse equals the final momentum, however way you want to look at that. Okay, so if we look at the differential form of this, we just get that the force is the time rate of change of the momentum. Right? If we want to think about the average force over some time period, the average force is the impulse divided by the time period. But it can also be thought of as the change in momentum divided by the time period over which this average force is applied. Another way to think of this is the change in momentum is the average force applied over some time period times that time period. All right, so now we can look at that's pretty straightforward for single particle. Now we can look at this for a system of particles. We have two kinds of systems, closed systems and open systems. Closed systems mean the total mass of the system is constant. So there's no flow in or out of the system of mass. With an open system, there can be. So if you think of a rocket engine or something like that, you're emitting from a rocket, you're emitting fuel out the back, and that's where the momentum comes from. And so that would be, if you look at the rocket itself, that would be an open system because its mass is changing and you're emitting mass into the surroundings. So let's look at closed systems. So we have a closed system of n particles. We can't add new particles or remove particles because then it would be an open system. So by definition, it's a closed system of n particles, and those n particles always constitute our system. We have some external force Fi on each particle. We have an internal force on each particle I due to particle J. And the impulse momentum principle for an individual particle, which is true based on what we just did, is that the external force plus the sum of these internal forces equals the time rate of change of the momentum for that particle. So this is the differential form of the impulse momentum principle for a single particle. Now we know the total force is the sum of all the forces on the particles, and the total momentum is the sum of all the momenta of the particles. And we know that the sum over all particles of all these internal forces is zero because we have the equal and opposite forces on each particle. So the force on 1 from 2 is the same as the force on 2 from 1, and so those cancel in a vector sense when we add them together. So if we do that summation, all those internal forces drop out, and we just get F equals P dot. So the total force on a system of particles, a closed system, is equal to the time rate of change of the momentum of that closed system. Okay, the momentum of a closed system of particles is the sum of the individual momenta, and it's equal to the total mass of the system times the velocity of the center of mass. Okay, so we can write that the total force on a system of particles is equal to the time rate of change of the momentum of that system, which equals the mass times acceleration of the system, just as we found before. Okay, if we write this in integral form, we find that the impulse of the total force, net force on the system, integrated from T1 to T2, is equal to the time rate or the change in momentum from the initial state to the final state for that system, the closed system. Now we can talk about conservation. If there's no external forces on a body, then the impulse is zero because this external force is zero for the system. So there is no change in momentum, right? So momentum is conserved when there's no external forces on a system of particles. Right, and that's called the conservation of linear momentum, and it's something again we use often to solve problems. Okay, so let's look at some example. First one is some world's strongest man competition where a guy attaches a rope to a jet and pulls on it, and it's a Boeing 737. He pulls it over a distance of 82 feet. It weighs 75 tons. The competitor can apply a force of 850 pounds at the beginning, and then he gets tired, and his strength decreases linearly by about 30% over the distance traveled, and it takes him 40 seconds to do this. So, question is, how fast is he moving, or is the airplane moving at the end? All right, so we model the force as a linear decreasing function of time. So we're given that the force on the airplane drops from 850 to about 600 over 40 seconds. So this is force versus time. We can integrate this over that time period, 40 seconds, to get the impulse. And by knowing the impulse, we can get the change in momentum. The initial momentum is zero because it starts from rest. So we can find the final momentum, which gives us the final velocity of the plane. So here it is. The initial momentum plus the impulse equals the final momentum. The initial momentum is 0. Okay, it starts at rest. V1 is 0. There it is. And then the force is given by this. So we can just put that equation in here, do the integration, and that tells us the impulse. So we just do this integral, set it to mv2, and solve for v2, and we end up with about 4 miles per hour. So by the end of this pole, 40 seconds poling with the force distribution shown, the plane is moving at 4 miles an hour. Not exactly light speed. All right, here's the next one. This is kind of like a problem we did a while ago. Before, it was a woman in a canoe or something, and now there's a man on some kind of a platform. The platform floats, so it's touching a pier at t equals 0 with the person at the end of this pier. Person walks to the other end of the pier from point A to point B. But since he's moving that way, the force from his feet on the platform moves the platform the other way. The question is, how big a gap um, is there between the pier and the end of the platform when the person gets to point B? And we can do this with conservation of linear momentum because there's no external forces on this, at least in the horizontal direction. There are some forces in the vertical direction, but the net force is 0, right? The buoyancy is counteracted by the weight, so there's no net vertical force. So there's no net external force on this body at all, and so we can conserve linear momentum and solve the problem. All right, this kind of talks about all that. So here it is. We set up this little coordinate system, x positive to the left, y vertical. We let xp be the distance from the pier to the person, fp be the distance from the pier to the platform, and we conserve momentum. All right, so in the x direction, the momentum initially is the same as the final momentum. Okay, so the momentum at T1 is the mass of the platform times the velocity of the platform plus the mass of the person times the velocity of the person. And the final velocity looks similar. You just use the final velocities instead of the initial velocities. And the kinematics are such that the velocity of the person equals the velocity of the um, platform initially are both 0. So we start with both of them stationary, and then the person starts walking. So the initial momentum is 0. So that means the final momentum has to be 0 because we're conserved. So the momentum of the person in one direction is balanced by the momentum of the platform in the other direction. So we can also look at this with a relative velocity approach. The relative velocity of the platform is the velocity of the platform is the velocity of the platform relative to the person plus the velocity of the person. And if we ignore the vertical motion, then x dot of the platform is minus v naught plus x dot for the person. So we can let that will tell us the relative velocity between the person and the boat. Okay, so that's v naught. So if we set v naught to be the length traveled of the person relative to the boat and divide that by the time it takes to get from one end to the other, then that'll give us that relative velocity. And then if we flip it around, we can solve that for the time. All right, so we can put those things together to find out that gap. All right, so we as I said, the final momentum is 0. So 0 is the final momentum of the platform plus the final momentum of the person. So that means the velocities of these two are of opposite sign and proportioned relative to their masses. The kinematics tells us that the velocity of the platform is minus v naught plus the velocity of the person. So we can substitute this in up here, get rid of the x dot fp2, and so this is just an equation for x dot p2. X dot p2 relative to v naught looks like this. Okay, but then the time it takes to do this is L over V naught. So we can solve um, for that from this and this. All right. We put all that together and it says the X for the person when he just reaches the boat is M over MP plus MFP times the length of the boat. All right. So the result is dimensionally correct. Those masses cancel. Um, it tells us that the bigger the person, the farther from the pier the platform will end up. All right. So that's a couple quick examples of how to use the impulse momentum to solve problems.